Now that we've given you a few examples as to how to mill and what the particular cutters are capable of, let's take a few minutes and go over the types of materials that you're likely to encounter. Remember, if we're going to be building a quality part, it needs to be made out of quality material as well as have precise tolerances. Let's go over some of the materials you're likely to experience. Mild steels, alloyed steels, stainless steels, aluminums, tool steels, cast irons, brass and copper, plastics such as Delrin and nylon. In the mild steel category for building parts, washers, bushings, different things of this nature, the 1000 series of material works really well. There's also some good leaded materials like 11L17 that machine really well. You get excellent cutter life, you've got high feed rates, you can really process a lot of parts in these materials. It's a non-critical material, it's not something that we would be heat treating. It's just spacer blocks, tooling fixtures, things of that nature can be made out of mild steels. Next, let's take a look at alloyed steels. These are usually our higher chromium-based steels, such as 4130, 4140, 41L42. The L designates some lead in the material, so it machines a lot better, and 4340. These are probably some of the most popular types of alloyed steels that you're going to be working with in the machine trades. They machine reasonably well. They heat treat up to 45, 48 Rockwell, depending upon the one that you choose, and are very popular for race car parts, parts that have a high stress application where we need a good high tensile strength and surface hardness. Many of you may be wondering, well, what type of cutters do I need to be using when machining these types of materials? For all of our mild steels, high-speed, cobalt, and carbide will work just fine. When we get into the alloy-based steels, 4130s, 4140s, 4340s, and just their normal annealed or normalized conditions, high-speed cobalt and carbide will work fine. If we have a heat-treated material such as 4140, 4340, where the Rockwell or the hardness of the material is above 38 to 40, carbide is usually the preferred tool under those applications. Otherwise, we're going to be wearing out the high-speed cutters and have them in the grind shop for touch-up. When we start machining stainless steels, 17.4, 416, and the 300 series stainlesses are by far the most popular. 17.4 is probably the best in terms of corrosion resistance. A lot of people whine and complain about machining 17.4. My experience has been if you use proper fluids and good sharp cutting tools that it machines just fine, especially in the annealed or normalized condition. 416 is usually a free machining type stainless. It's used a lot in the barrel industry. It has a reasonable amount of sulfur in it, so it does machine well. The 300 series of stainlesses, 303, 308, are also good materials. They will heat treat up hard. You want to watch on the 300 series. Keep the cutter moving across them. Use a good cutting fluid in that process. Anytime that we use a 17.4, which is a precipitation hardening stainless steel, anytime its Rockwell exceeds 40, again, carbide is probably the best choice. You can do it with cobalt, but you're going to get some squeaking noises. You're going to need to apply a lot of fluids anytime the Rockwell gets around 40 in that specific material. Next, let's take a look at aluminum. The majority of our tooling fixtures are going to be built out of aluminum. 2024 is an excellent tooling plate material. You'll have a hardness designation of T351 on it. Anytime in aluminum, we're going to be dealing with 4 specific numbers. That is the alloy of aluminum that we are using. The last number, T351, T6, T751, those are the hardnesses of those specific alloys. 6061 is an excellent material. It has a tendency to be a little gummy by comparison. I really prefer 7075 and a T6 hardness. It machines really well. It anodizes very well. That is my preferred material if I'm building toolings, jigs, and fixtures. Let's take a look at tool steels. If you're lucky enough to get a job in the mold making industry, you're going to be dealing with a lot of tool steels. D2, H13, F7, and A2. D2 is probably one of the toughest type materials that you're going to machine. You're going to use carbide cobalt cutters in most applications there. It's a very abrasion resistant material. S7 has good machining characteristics, very tough, durable material. If you're going to be building a part that's under a tremendous amount of stress or taking impacts, S7 is an excellent choice. Cast iron, we talked about that in our lathe series for those of you that watch that. Cast iron, we want to be really careful when we're clamping it on the table, not to put it under any stress where it's going to crack. We do not use any cutting fluids at all in cast iron. Carbide makes an excellent cutter choice when we're machining cast iron. Brass and copper, those are a couple you need to watch out for. They machine well. Copper, on the other hand, though, is a very sticky, grabby substance to machine, and you do not want to get too aggressive in the feed rate when we're machining copper. It has a tendency to want to suck the cutter into itself, especially under climb cutting conditions. So take your time, be careful with the copper. Don't use any fluids on the copper. On the brass, we can use a little bit of soluble oil. Seems to work pretty well. Plastics, we have Delrin and nylon. A lot of bushings, different hubs, things of that nature will be built out of a product called Delrin. More of a trade name. It's a nylon base type material. Machines really well. Again, we wouldn't be using any cutting fluids on the plastics or nylons at all. We want to use a 2-flute cutter, turn the RPMs up pretty high. Remember to put a radius in the corner a lot of times when we're machining with the nylons. Gives us a little bit extra strength. That pretty well concludes a lot of the materials that we're going to ask you to work with. If you desire more information on the specific types of materials, your local steel supply houses are capable of providing you with a book such as this one from the Earl M. Jorgensen Company. They're going to deal with the different steels, aluminums, and alloys that were quite popular in the machining industry. Let's take a look at the aluminum section and see what we find. Remember, we talked about 2024 aluminum. It's going to give us the color markings on the rod and a bar. The ends are usually painted red. This is one of the best known of the high-strength aluminum alloys. With its high strength and excellent fatigue resistance, it is used in advantage in structures and parts where a good strength-weight to ratio is desired. That's just part of the information that's available on 2024. Let's look at some additional information. We have specific applications, primarily used in the aircraft industry for structural components, tooling, truck wheels, etc. It also will tell us the machinability of this specific alloy in its different heat treatments. It'll also show the heat treatment of the material. Remember the T designations after the 4 numbers of the alloy, T3, 4, 361, etc. Look at the tremendous difference from the standard mill run or annealed condition with a tensile strength of 27,000 psi and a yield strength of 11. Now in a heat-treated condition of, let's say, T361, that same tensile strength goes to 72,000 psi and the yield to 57,000. So approximately 3 to 5 times the strength when we heat treat that alloy. You can see how valuable of a reference source these types of books can be. Now let's take a look in the machinery handbook at a different type of alloy. Like the Jorgensen catalog, the machinery handbook is an excellent source for information. One of the things I like best, we can look under specific steels and applications, and they make a recommendation as to the type of steel. Let's take a look at forgings that are heat treated. 6150 is the suggested material. If we're going to be doing gears that are carburized, 3120, 4125, 4320 are, again, excellent choices. Moving down to the bottom of the page, we can see gears, gear rings, gear transmissions, an excellent reference source if you have a specific application that we're trying to match. Simply consult the machinery handbook, look up the designated material, get on the hot phone, call up the local steel supply, and order a truckload for your next machining job. There is a wealth of information in the machinery handbook. Take the time to read it and become familiar with it. It will answer a tremendous amount of questions that you may have on alloys, machining operations, etc. Keep in mind that in different types of alloys, they're going to be color-coded on the end of the bar. Consult your local vendor from whom you are purchasing, and he'll be glad to give you the color code reference charts. Another thing I like to do is go to the local steel suppliers in the area. Usually they're going to have a rem pile that's filled with cut-off ends anywhere from 6 inches to 2 foot long. You can also buy aluminum plate and steel from these same vendors. It's a good idea to pick up a truckload of this next time you're in town because it's an invaluable source and it saves and makes you a lot of money in the long run. If a customer comes in and he needs you to machine a part 6-8 inches long, you're going to have to call up and buy a 20-foot bar from the local vendor. Again, this is money out of our pocket. If we want to use materials for a piece of tooling plate or a little jig and fixture, having our little bone pile in the corner can be an invaluable resource. Keep those things in mind the next time you're at your tool steel supply house. I don't know about you, but I'm getting a little antsy to start making some chips. We've covered a lot of the basics, different machine operations, the types of materials used. Now let's show you the proper way to prepare that piece of stock for a project. We've got a piece of tooling plate that we cut 1.25 inches thick by 2 3/4 by a little over 4 inches. You can see when we cut it off in the saw, we've got a rather large burr here. And this is part of the stock prepping procedure. We simply wouldn't cut it off, set this material in the vise, and go to work on it. We're going to take a file, 6/8 inch single cut file, works really well, and we'll go around all of the edges of that material. Remember to push the file at approximately 45 degrees to the part. The file cuts on the forward stroke. We're going to go through and basically burr this entire block, so when we set it in the mill vise, we don't have any burrs, nicks, or dinks affecting the parallelism of the part. You can see we've got a big dink here, so we're going to use that as our first cut to machine that away on the top. Take your time during the stock prep. It's very important when we get ready to square and true up the block that we've done this. Each time that we make a cut on the part, we want to check it for a burr. We don't want to be switching back and forth and forget that we've got a big burr on one side that will later affect the accuracy or trueness of the part that we have. Take your little paper towel, wipe the filings off of the block, and then I get in the habit of just running my hand over the block from time to time, making sure that I haven't missed anything, okay? We can take our file and run it over that surface, make sure it's flat. Usually the milled slabs that you see from the manufacturer are going to be pretty true, so we can use those as a baseline. Run our file over them, nice and smooth, remove any filings that we have left on the part. All right, so we've prepped this piece of stock. We're now ready to set it in the mill vise and make our first cuts in order to get it truly square and parallel. We want to wipe our vise jaw nice and clean. Again, we don't want to be setting it on any parts or chips that will cause it to not work off of the vise jaw. The rear jaw I like to refer to as the master jaw. We've dial indicated in, if you remember earlier when we mounted the vise, these particular vices are ground true and parallel within a couple of tenths of an inch. So they're very, very precise. We're going to set this block against the face of our vise. Now, if the block is not parallel or tapered, when we clamp it, it can be shifting in the vise one way or another, and you go, wow, that's a real problem. How do we overcome that? A neat little trick that's often overlooked by many folks these days is simply take a piece of round stock, put it in behind our block, where we're just pushing on the center of the vise jaw, and tighten it down, okay? We've ensured that this face is clamped securely against the face of the vise, and now we're going to go ahead and take a pass across the top of the block. We can do that with an end mill. We can do it with a fly cutter. Let's start with an end mill, and I'll show you a little trick to significantly reduce the amount of burr that we get on the part by cutting this in a climb cutting method across the top. You've watched a couple of times. We'll go over the final details of securing the collet in the chuck. You're going to have a little nubbin in the chuck that tracks off of the R8 collet. It's a little guide that's in the spindle that matches this slot to keep our R8 collet from spinning in the spindle as we tighten it up. So we'll simply insert it, rotate it around until it lines up, push it in place. We're going to reach to the top of the mill head, and we're going to finger tighten the drawbar to suck the collet into place. Once we feel the draw nut come up tight, we're going to insert our end mill, choke it up nice and tight, reach up with our wrench, and we've noticed the brake on the top of the mill. Okay, we're going to put the brake on as we tighten the drawbar. Get it pretty snug. We don't want to twist it off. We don't want to damage the collet. We're going to bring our cutter down in contact with the work. Okay, remember to keep the quill handle in the proper relationship. We don't want to be pushing forward with the quill handle. All right, and I like to start on one end of the part, so we're going to move the table in what axis? All right, the x-axis. We'll center up our cutter, bring it down until we just come in contact with it. We're going to lock our quill. We can go ahead and set our stop. Quill stop, run it up. You can see how I'm using my thumb. I've got about 1/4 of an inch spacing between the stop dial and the actual lock nut. And as I run my thumb across them, we're turning them up at both about the same level. So we're not playing chase. One locks into the other. Okay, we're ready to go. On this particular cutter, we're going to turn it at 1115 RPM. We'll advance it and just scuff the top of the workpiece. We know we're in contact with that. We're going to raise the bed of the mill 20 thousandths. We're going to take a 20 thousandths cut the first time. Rather than go down the center of the part, we're going to index over to the left, and we're going to cut around the periphery of the part, removing the burr from the outside edge. So we'll index our cutter over, give ourselves a shot of WD-40 across the top, and advance the cutter where we're just cleaning up the top edge, cutting into the top of the part, forcing the burr off of the part. In a production process, if we're doing a lot of these blocks, this will save us a tremendous amount of time in cleanup and burring. Okay, you can see that our block was out of parallel a little bit. We didn't clean up on that side. So let's go around to the other end. Okay. You're getting a little bit of an optical illusion with the cutter on camera. Don't worry about it. Just watch the direction of travel of the cutter. We'll go back and let's take another 20 thousandths off. Okay, in this fashion, the cutter is rotating clockwise. This would be a climb cut in a facing operation, okay? We're simply facing the top of the block off in a climb cutting motion, taking the burr from the outside edge, forcing it to the inside edge of our block. Run your cutter all the way to the end of the block rather than stop. Now index it over. We'll run back the other direction, and we're going to see a little center stripe start to appear in the top of the block where the two passes of the cutters intersected. Again, we're going in a climbing motion as we're moving the bed from left to right. Remember, we want to have a nice, slow, deliberate feed rate. As we become more advanced, we can go ahead and put the power feed on. But I want to get your basic mill handling techniques down. All right, now you can see we've got a nice smooth surface on the top of our block where we've indexed our cutter over, and by climb cutting, if we're to run our fingers along these sharp edges on the sides, we don't feel a burr. If we were to cut in a conventional method, forcing the material off in this fashion, it would raise a burr on the outside edge. So with this part surfaced on this side, simply remove our bar, take our vise out, or take the part out of our vise, and as a matter of habit, we're going to go ahead and take our file and just for practice, put a little chamfer on that outside sharp edge. Okay, usually 3 or 4 passes of the file. We'll try and give you a close-up view of that so you can see the width You can see we're just breaking that razor sharp edge with the file. Make sure and wipe the part off again because we've got little chips and stuff from our milling operation. Be sure and clean the vise out. If you don't have stock in a paper towel company, I strongly suggest you do it, that or the rag company, because you're going to be using a lot of rags, keeping the vise clean, keeping all of the chips out. Once I've done that, I like to take my thumb and just run it across the vise jaws, making sure that there's no residual chips left. All right, we're going to take our machined surface that we just machined. That's going to go into the bottom of the vise. This was the face or surface that we had against our master jaw. So we're going to want to repeat that as we insert our part back into the vise. Push it up against the master jaw. Grab our piece of round stock. Hold it down. Okay, and tighten our vise up. We don't want to scrounge down on the vise. The vise exerts tremendous holding force. Simply snug it up pretty good. And we're going to go ahead and resurface this top edge. What is that going to do for us? You guessed it. It's going to make those two surfaces parallel and to dimension. So we'll go ahead and take another pass across that. Then we're ready to square the ends of the block. Remember now, we've made our adjustment on our quill. If we're to run our cutter across the top, it's just going to barely skim the top of our part now. So we're going to raise the bed in the Z-axis another 20 thousandths of an inch. Give our cutter a little shot of WD-40 across the top of our part. With a nice smooth feed rate, advance the cutter across the top of our block, cutting to a specific height. Remember, on the knee, our dial is in 100 thousandths per revolution. On the cross feed, on the X and Y axes, our dials are in 200 thousandths per revolution. Index our cutter over, down the top of the part. It's a very light machining operation. Again, we're taking only 20 thousandths off and surfacing the block and bringing it into a desired dimension. Take our towel and again wipe our part off, getting a lot of the chips and stuff out of the way. Okay, we have our back reference pushed against our master block. We've created this surface and the bottom surface parallel and to dimension. Now we're ready to square the ends of the block. If we're to run our dial calipers, check that into the block. We've got 2 inches, 620 thousandths on this side. 2 inches, 620 thousandths on the other side, okay? Always get in the habit, again, of checking our part. If we were to get a chip inadvertently in the vise underneath the part, it would cock it, and those two ends would not be parallel. Okay, with our vise jaw clean, it's now time to insert a couple of precision ground parallels, and I'm going to show you another trick that I've learned over the years, and that is to keep the parallels in place. Simply give your vise a little shot of WD-40 or any other type of spray oil, and this allows the parallels to, in essence, stick to the jaw at that point, okay? They kind of bond themselves there with that oil. We can tug on them a little bit, and we can't break that bond. Make sure that your parallels are nice and clean and they're free from any nicks or dinks in them that may affect the accuracy or parallelism of the part that we are setting on top of them. I like running them back and forth once I mount them, and this allows you to feel any clinkers that may be underneath the parallel. Okay, so just get into that habit again. It's stuck to the vise jaw with the WD-40. Go ahead and open our jaws a little bit. You can see now that we have a depth of approximately a ½ inch here. The depths of these jaws are 1.5 inches. So we've got a ½ inch of our master jaw to set it against. We're going to go ahead and set our block in. In this fashion, we can retract our parallels a little bit because we're going to go ahead and square this surface now. We dialed in the back surface of our master jaw, so when we work off of the y-axis, what is going to occur? This surface and this surface are going to be exactly 90 degrees or perpendicular to one another. This is how a mill works. A mill makes things square and perpendicular to one another. Just like the lathe turns things in a round, cylindrical fashion, faces them off square, etc. Okay, so we're going to protrude about a ½ inch outside of the vice jaws. We want to take and push our part down on top of the parallels and slowly tighten the jaws. And you'll see that we tightened it and we loosened it a little bit. This allows us to feel what the part is doing when it comes under clamping pressure. If we start to clamp the vise up and with our fingers on the top, if we feel the part start to drift or tilt, we know that something's wrong. At that point, stop, check everything, make sure that we haven't found a chip that's worked its way underneath the part, affecting the accuracy and layout of the block as we put it in the vise. Everything feels really good, and this is about the minimum that we would want protruding above the vise jaws on a part this thick. Okay, we wouldn't want to mount it in the vise where we just had, let's say, a 1/16 of an inch of grip on the parts. Okay, that's not a good idea. Try and get as much surface contact on the vise and on the part that we're dealing with, so we've got a good, what? You guessed it, a good secure hold on the part. Okay, we'll take our cutter. We're going to raise the bed up a little bit so we don't have to extend the quill down nearly as far. Move the table in the x-axis to get the cutter over on the side. Okay, we can go ahead and lower the quill at this point. Run the cutter up on the side. Make sure that the cutter protrudes below the thickness of the part. We've got a little bit of a radius ground on the edge of the cutter, so again, you want to make sure that that radius extends below the part so we get a real nice flat surface. We don't want a little bit of a radius being machined on the bottom of our part, which will overall affect the squareness of things. Once this is in position, go ahead and lock down the quill, and we'll turn the cutter by hand now. If we're cutting, you can see the cutter rotating this way. If we're to move the cutter this direction, that is in a climb cutting mode. And anytime we take climb cuts, we want to have a very small amount of chip load in the cutter at that time, because what's happening is we advance the workpiece into the cutter. It's trying to walk its way along or climb its way along the top of the part that we're machining, and this can be rough on the machine. If we're to take a real heavy cut and we try climb cutting across that and have a real fast feed, we can literally shear off or break that cutter as it becomes really aggressive trying to grab more material. If we were to turn this direction and pull the cutter this way, this is called conventional milling. Okay, we're scooping the work out. The work is resisting the thrust of the cutter as it's being fed manually by the table across the part. We can go both directions to remove a maximum amount of stock, but the heaviest amount of removable occurs when we are in the conventional cutting mode. Okay, watch, we'll show you both methods. Bring our cutter over to the end, come in contact with our part, index over, desired amount of material that we want to face off, and look at those long chips just peeling off of the part, okay? This is conventional milling now. We're forcing the cutter into the workpiece. We'll change directions now and take a climb cut. We'll take maybe 5/10 thousandths at that pass. Again, the cutter is climbing its way across the part. It's going to give us a little superior finish along this line, so when we make our final dimensioning, we can take the last 5 or 10 thousandths off in a climb cutting mode. Notice the chips coming off are a lot finer than they were when we went into the conventional mill. We were removing a lot more material. Okay, we've got a beautifully machined, slick, polished finish. It almost looks like we ground it. We've got a good sharp cutter. We used a real good lubricant. Even though it's cheap, WD-40 works really well. And now if we were to check the back surface with the surface we just machined, those two would be perpendicular to one another, exactly 90 degrees, because we moved them on the XY axis. Okay, so now we can turn our part around, machine the other side. Be sure that we clean all of the chips off of it. We don't want this to affect the accuracy of our block. We're well on our way now to getting a part ready for the final machining process. Take your paper towel, wipe those parallels off. Another advantage to putting the WD-40 on the parallels is that it seals them up against the vise jaw, and we do not get a chip in on the back side of them. Make sure that we wipe our hand across the part, checking for any chips or debris that may be there. Check both sides that we're going to be clamping in the vise jaws, and very carefully set our part down. Put our fingers in the top, pushing it down, and tighten our vise, loosen our vise, and see if we can feel any shifting in the part. This is very, very important. Okay, hit it with the heel of our hand, lock it up, advance our cutter down, and we're ready to take another conventional mill cut in the roughing removal of our stock. Come in contact with the work, index over, take another 20-30 thousandths. We're going to conventional climb, removing the bulk of our material. Now we're going to come back with a climb cut, 5 to 10 thousandths for our finished pass. Listen to the machine. We've got a very uniform throbbing of the cutter as it's removing material from our aluminum block. If you hear any abnormal noises or it sounds like it's crushing rocks, stop and see what you're doing wrong. Either we're taking too much material in the cut, we've got insufficient RPM in the cutter relative to our feed rate. There's a balance that we achieve here. We're going to show you a formula a little bit later on that tells you specific feeds, RPMs, feed rates, etc. But again, as we mentioned earlier, when we're dealing with a step-pulleyed Bridgeport mill, we're dealing with specifically 8 speeds, 4 in back gear, 4 in direct drive. So those speeds have been chosen by the manufacturer to be the most versatile for the different diameter cutters that we are using. You're going to find that for most of the cutters that you're dealing with in general machining operations in direct drive, 660 to 1115 RPM are about optimum for cutters up to 3/4 of an inch, again depending upon the type of material and the hardness of the material that we are machining. Alright, let's wipe our aluminum block off and take another look. Alright, we've got another beautiful machine finish at that point. Alright, now it's time to surface the top of our block that we have setting in the vise. But first we're going to need to remove our cutter and replace it with a fly cutter. Remember, we used the fly cutter earlier on. It's a larger diameter cutter where we can surface the top of this part in one pass. We don't have to take the end mill and run it back and forth across the top. We'll get a much more uniform and consistent surface finish as well. We've showed you how to install the cutter. Now, here's a couple of tips and tricks on how to remove the cutter and replace it with a fly cutter. We're going to reach to the top of the mill and apply the foot or hand brake. Put our wrench on top of the drawbar. With the brake on, we're going to go ahead and break the cutter loose. Once we see the wrench is starting to turn freely, we can loosen our grip on the hand brake. We're going to reach down and with our index finger and thumb, grab the cutter as we continue to loosen the drawbar. Once the drawbar is loose, I like to take the wrench, or you can take a plastic hammer and simply tap the top of the drawbar, and that breaks loose the collet from the cutter, separating the two for removal. Take your right hand, take your middle finger, put it on the collet with the left hand at the top, and we're simply going to spin the drawbar off, releasing the collet from the spindle. Okay, very important. Don't drop the collets. Don't drop the cutters on the workpiece. If you're dealing with a carbide cutter and you drop it out of the collet on the workpiece, there went a $40, $50, $60 cutter because it's going to chip and break. Make sure that we've removed all chips from the R8 collet when we get ready to install the other one. Insert it, rotate it until we find the guide, reach up, Engage the collet with the drawbar by turning in a clockwise fashion, and we're now ready to install our fly cutter. Choke the fly cutter up nice and tight. We want to have good rigidity in any cutting operation that we engage in. You can see we've got about 3.5 inches of depth between the fly cutter and our surface part. We can go ahead and raise the knee, again keeping a very rigid setup while we're machining this. You can also bring the quill down if you want. I like maybe bringing the quill down an inch, inch and a half. We're going to bring the cutter down towards our workpiece with the quill and watch until the cutter just comes in contact with the top of the workpiece, okay? At that point, we're going to reach over and lock the quill down. We're going to go back to the knee and our Z-axis, and in a counterclockwise motion, we are going to lower the table 5 thousandths. So now if we advance the cutter is not scuffing on the top of our part, okay? We'll do this once the cutter is running and we're ready to advance it into the workpiece. Remember, when we're using a fly cutter is not for rapid removal of a lot of material. It's simply to surface the material. A heavy cut with a fly cutter is usually 50, 60, 80 thousandths, not much more than that, depending upon the type of material that we're doing. Very fine amounts of material can be removed in order to surface the top of the block. So we're going to go ahead and back the cutter away from our block. Okay, we've got clearance now, so when we turn it on, we're not ready to cut. We're going to go ahead and advance the cutter over the top and very gradually raise the table to the 5 thousandths that we did when we lowered it. Okay, so now we're in contact with the block. We've started cutting. We're going to take about 3 thousandths off the top, shoot our block with a little WD-40 and on the cutter, and with a very smooth, uniform motion, advance the cutter across the top of the workpiece, creating a mirrored polished surface. Okay, remember we want nice, smooth, uniform advancement of the table and the fly cutter across the part. We're rolling the dial in the palm of our hand, just like it was on a power feed. All right, with that complete, we'll turn off the mill, wipe our part down, again clean the vice jaws, and we're ready to flip the part over and surface the other side. Okay, before we do that, for those of you that have your thinking cap on, what is our next procedure? You guessed it. We're going to run a file across these edges, making sure that we don't have any burrs on that part. So very gently push the file across at approximately 45 degrees and just break that razor sharp edge that we've created. Want to have a nice, smooth, uniform facet on all of the sharp edges on the block. We don't want to have it real thick on one end and trail off to nothing on the other side. Okay, once we've done that, take our paper towel or rag, wipe our block off, getting rid of any chips or debris. Take the palm of our hand. It's amazing what you can feel with the palm of your hand. Don't always take for granted that just because we've wiped it off with the rag that it's absolutely spotlessly clean, because it will not be in many cases. Set our block down and go over and make sure that our vice jaws are clean. Also, once your rag or shop towel becomes saturated with chips, it's a good idea to trade it in on a new one, okay? Every now and then the gremlins will start playing with your head, and as you wipe the towel across it, it just deposits little chips behind you. Okay, so we're going to push down with our left hand, tightening the vise with our right, break it free and see if we can feel any disturbance or shifting of the part. This feels really solid. Go ahead and tighten down our vise. Turn the machine on. We're going to come back in the other direction with a 10/1000 cut. Lock our knee down. This is our final pass. Give our part a shot of WD-40 and very slowly advance the cutter. I always like watching the stream of chips coming off the cutter. Reminds me of a machine gun in action, just kicking those empty cases out, maybe on the charge of San Juan Hill. This is a good indicator as to whether your head is trammed in as well. When we bring that cutter across, we're going to have a nice uniform trail picking up our cutter as we go across, creating a nice uniform finish. All right, there we go. We've now created a block that is gauged to sides. All surfaces are parallel and square to one another. This block is now ready to machine a part from. It's very important that we start off with a good reference material. If we were going to machine 100 of these parts for second and third operations, and we were to set up a work stop in the mill, they have to be the same size. If they're varying 5, 10, 15 thousandths because of sloppy machine tendencies or workmanship on our part, the result's going to be scrap as we start to put them into a master or run them up against a work stop thinking that they're all the same size. Take your time. Make sure that all of our setups are spotlessly clean. We don't have any chips or debris that may affect the placement of our block. Make sure that we take our file. We go over all of the sharp edges that we've created in the squaring and truing of our block. Okay, that pretty well covers the squaring and truing operations. Let's move forward. Oftentimes we're called upon to perform a second or third machining operation on an existing part. So it's very important that we understand how to properly set that part up, make different locations based on that part's length, diameter, width, etc., so we can get a hole in the right place, machine a slot in the right place. As an example, we're going to take this round cylindrical piece of aluminum tubing. The customer has requested that we find the center of it, drill a hole in the center of the part in this dimension as well as this diameter. Now, a problem comes to mind. Many of you will say, all right, well, we'll just set it in the vise this way and clamp it. Well, two things can arise in this particular application. One, if we tighten the vise too tight, we can simply crush this piece of tubing. But most importantly, we don't have any place to get at to really measure. We could come back off of our master jaw with our edge finder and kiss it this way and then move into the center. But I think a better way to hold this particular part is to simply turn it in the vise this way. All right, this allows us to measure off of an exposed area here as well as on this side. So we've got two uninterrupted areas that we can bring our edge finder against in order to locate the edge and thereby the center of the part for our drilling operation. This particular tool that I'm holding in my hand is called an edge finder. Very important tool for the machinist. These little nubbins that you see on the end are held together in the body by a long extension spring. So as we run it up against the part, it starts running true, and then the moment that we hit the part, you're going to see it jump in an offset mode this way, indicating contact. All right, the diameter of our edge finder is 200 thousandths. This is usually a standard. So anytime that you're dealing with an edge finder, run your dial calipers or micrometer over the end to determine the diameter of it. As we bring our edge finder up to the part and it makes contact, you'll see the offset kick in. Okay? At that point, we've made contact, and we can go ahead and adjust our dial, whether we're using a digital readout or, in this instance, we're going to go ahead and use the X and Y axis and loosen the dials on the bed in order to perform this operation. So if our part were 2 inches thick, the center of it would be 1 inch plus the 100,000ths offset that we have in the edge finder. So we would move the part over 1 inch and 100,000ths from our contact point to locate that hole exactly in the center. It'll become a lot easier for you to understand once we show you the actual process. We're going to grasp this in the Albrecht keyless chuck. The body diameter is also 3/8 of an inch in diameter, so we can grab it in a collet. But a drill chuck is the obvious holding method because we're going to follow it up with the center drill. Let's take the dimensions on our part and start to calculate where our center line is going to be. Using the dial calipers, we've got a dimension of 1 inch, 250 thousandths. So half of that is 625 thousandths plus the 100 thousandths for half the diameter of the edge finder. So from either edge, the amount that we would move the table in the y-axis is 725 thousandths. We'll work one dimension at a time. Watch closely as we show you the offset when using an edge finder. Even though we're not cutting, it's a good idea to put on our safety glasses during this operation. We're going to move the table, advance the quill down to where we can see our edge finder protruding over the lip that we want to contact, lock the quill down, and very slowly advance the table or the edge finder towards our part. You can see the offset taking place when we come in contact with the part. You want to have a very gentle touch here. You don't want to work it in really quick and break the edge finder or pull it off the spring. Be very gentle, and as soon as we see it offset, at that point, we're going to lock the gib down on the y-axis. We'll loosen the lock ring on the dial, advance the dial to 0, hold it in place with the left hand, and then finger tighten our lock ring. This gives us an accurate setting. Now we'll raise the quill, moving the edge finder out of the way. We'll slowly go back to our dial now, and we're going to advance the table 725 thousandths. Remember, in the X and Y axis, each rotation of the dial is 200 thousandths per revolution. So we've got 200 thousandths, 400 thousandths. Watch our knob. This is a good counter that we can do each time we rotate it. 600 thousandths, 700, 5, 10, 15, 20, and 25, stopping on 75. Now it's time to lock the gib down on the y-axis of the machine. We'll turn our machine off. We'll take another dimension as to the diameter of the part. 1 inch, 740 thousandths. We're going to divide that by 2, so that is 870 thousandths plus the 100 thousandths for the edge finder. We're going to advance our table on the x-axis, bring our edge finder down to where it just goes past the center line of the part. Remember, we always have to work off of a diameter or an edge of a part with the edge finder. Now it's real critical that we don't get the body of the edge finder up against the part, because this is going to give us a false reading. We simply want our 200 thousandths diameter lug to be the indicator. So be very careful in the placement of that. Lock our quill down, turn our machine on, and again, watch for the offset as we come in contact. All right, we can see the offset appear right on the edge here where my fingernail is. We're running flush, there we see the offset. At that point, as soon as we see the offset, we know that we've made contact. We're going to reach under the table, lock our gib down, locking the table into the x-axis. We're going to loosen the lock ring, rotate our dial to 0, lock the lock ring down again, loosen our gib. We're going to go back to the edge finder. We're going to raise the edge finder above the work and advance our table now the desired dimension, which is 970 thousandths, 30 thousandths less than 5 revolutions, okay? So we've got 200, 400, 600, 800 thousandths in 4 revolutions, 900 thousandths and 70. So we're going to stop on 30 right at that point, okay? So we've advanced the table in the x-axis. We're going to lock our gib down at that point, and now we're ready to center drill our hole. Remove our edge finder, install our center drill, and let's take a minute and talk about center drills in the milling operation. We have different sizes of center drills. This is a double-ended center drill, as most center drills are. Anytime that we're using a keyless chuck, keep in mind that we have a plate that comes down and secures the point on top of the center drill. So when we install the center drill in the chuck, we want to bring the chuck in contact with it, push it all the way to the top, and then pull it down maybe 30, 40 thousandths, so that plate that's coming down on top of the chuck does not dull the top cutting edge of our center drill. That's a mistake a lot of people make. They push the center drill in, they push it all the way to the top of the chuck, and then they really put the pretzel hold on it, tightening it, and it's what happens. That plate's forced down against the top cutting edge and it dulls it, and we've lost a cutting edge on that surface. So with our center drill now, okay, on the center drill, you're going to see we have the little spot tip here, and we've also got a 60-degree angle here. This is what's going to guide our secondary drill after we've spotted it. The center drill is a very short, stiff drill. It's used for locating that first hole. It doesn't walk and drift as if we were to use a long conventional drill. So watch closely now as we perform a center drilling operation in the mill. Turn our machine on. Going to bring our drill down in contact with our part and very gently pull the quill down. Now we're just starting to cut into our 60-degree chamfer. We'll go ahead and retract our drill. Okay, you can see now that we've got a nice cone-shaped hole that's going to guide that second drill as we come in and bring our hole to size. This is very important that we come down into that bevel, not just come in and spot it on the top. Okay, we're going to use a number 7 cobalt drill. When we're worrying about a drill now, it's important that we push it to the top of the chuck where that plate comes down and compresses it, holding it securely. It's only when we use a center drill that we want to retract it just a little bit so we don't damage the point. Okay, we're going to go ahead and adjust our quill handle because we've lowered the table. We want to be in the proper position, as we showed you earlier, to pull the quill down and not force it underneath, whereas if our hand slips off, we fall into the cutter or our machine, okay? Go ahead and turn it on very gently, start the drill down. Drill all the way through, retract our drill, hit the handbrake. You can see how fast an Albrecht keyless chuck is. We can drill a lot of holes in a hurry. We're not fumbling around for the chuck key, scraping our knuckles, trying to get the drill out and putting another one in. For production work, the Albrecht keyless chuck is the #1 chuck for your milling and drilling operations. All right, so that's one method of finding the center of a part, drilling a hole, using an edge finder. Now, let's take a look at, again, another type of setup and the complications that it may afford in a machining operation. Let's take a look at the use of a secondary vise clamped in our primary vise. This is our little toolmaker's vise that we talked about earlier. We've got a piece of 11L17 bar stock mounted in it, and the customers requested that we cut a 30-degree sloping angle on the end of these parts. Apparently it's some kind of a key slide that he is using in the manufacture of another part, and he needs a precise angle machined on that. So by grasping the part in the vise, we're simply going to set it in our other vise and use what is called an angle block. This is a precision ground block at 30 degrees. We're simply going to set it in underneath the vice jaws here and set our vise on top of it. Okay? Make sure that it sets nice and flat underneath here. It's just a little gauge spacer block is all we're setting it on to dictate the angle of our vise. Okay? Just seat our vise with the heel of our hand, go back and loosen it up, check it, make sure everything's fine, give it the final tightening operation. Now we're going to be machining a piece of steel now. Up till now we've been machining aluminum. So we're going to want to adjust the speed and feed rate because we're dealing with a little bit harder material. We also have a lot of material exposed out of the vise, so that's something that we need to keep in mind as well. We want to take some relatively light cuts as we surface across the top of our part. We're going to raise our table up, giving us a good rigid cutter position. You can see that we've choked the cutter up pretty far in the collet. We don't have a lot of exposed cutter protruding down from our collet. It's a 1/2 inch diameter collet in steel. Let's go ahead and adjust our speed now to 660 RPM. If we were taking light cuts, we can probably cut it at 1115, but 660 is a little bit better speed for what we're doing. Okay? Bring our cutter down. We're going to lock the quill down and index the cutter just over the edge of the part. We're going to raise the mill bed till we just come in contact with it, back the cutter away. We're going to take about 50 thousandths at a pass. Very gently advance the cutter across the part. Okay? Take another pass. Again, listen to the machine. We've got a nice smooth sound as the cutter is working across the part. It's not going clackety clackety clack, indicating that we're machining at too high of an RPM or too fast of a feed rate. Okay, when you have a lot of material exposed, as in this case, you want to have a very slow feed rate. We don't want to hob across it really quick, tearing the part from the vise. Okay, we're just about there, and remember, this is kind of a climb operation relative to the top edge of the part. We're removing the burr off in this process. Index our cutter over. Come across it for the second pass. Okay, about another 20 thousandths ought to do it. You can also watch the chip color. You can see the chips are coming off in a nice shiny color. They're not turning straw or blue color, again, indicating too high of an RPM or too fast of a feed rate. We're not using any cutting fluid on this particular job. We're machining a leaded type material that machines really well. Okay, there you have it. We've surfaced that at 30 degrees. Done a real nice job. We've showed you a little different type of material now. That was a piece of steel, 11L17. Nice piece of free machining leaded steel. Got to turn it on the side there, and you can see the angle that we've machined on it. So you can see the versatility of having a couple of vices around and how to mount them in our main vise on the table. Now let's take a look at indicating in, by the use of the edge finder, our machined block of aluminum for a hole pattern or for a slot. Just another example of how to properly use the edge finder to locate the position of a hole, a slot, or a rail that we may want to machine. All right, it's important again that we clean the vice jaws really well. We've got our nice polished surface block that we worked on a little bit earlier, and we don't want to damage or mar it by having some chips in the vise or chips on the part as we tighten the vise up, embedding the chips in those parts. If you're doing a lot of finish work that's to be anodized, painted, black oxided, it's real important that we treat the exterior finish of the part very gently. The customer really gets ticked off if he's got some really nice ground parts and he sends them to you for a second or third operation to be done, and you muck them up by clamping a bunch of drill shavings into the sides of his part, okay? So take your time. Again, we want to have pride in our work. We want to make sure that everything we do is the best that we can possibly do. We don't take any shortcuts. We don't turn out any shoddy work simply because we've got a hot date that night with Susie Q. Do it the following day. All right, we've secured our part in the vise. We've tightened the vise jaws up. We've pushed down with our fingers, loosened and tightened the vise. Everything feels really solid. We'll go ahead and replace our cutter now with the edge finder, and we'll make some more calculations as if we were going to drill a hole in the top of our part. Always get in the habit of snugging down the edge finder in the collet. Just don't finger tighten it. Okay, we want to get a real true reading now. We'll take our dial calipers. We're going to measure, we're going to cut a slot down the top of this, just as an example. The width of our part is 1 inch, 245 thousandths. So we're going to take and divide that in two. That's going to be 622 and a half thousandths plus the 100 thousandths offset for the edge finder. So our total dimension is, for the price is right, 722 and a half thousandths in order to get our spindle directly over the center of our part. All right? Turn the machine on. Don't forget to throw your safety glasses on. Going to bring our edge finder up very gently until we just see the offset. Okay? At that point, we're going to lock down the gib. We're going to come over to our dials again. We're going to loosen the lock ring, re-zero our dial. Stay focused on the dial right now. I'm just going to go up and raise the edge finder, and we're going to advance the table in the y-axis now, 722 thousandths, 200, 400, 600, 700, 10, 22. And as we get up on those half thousandths, I like to stop just shy of it and just take my knuckle and tap on the hand wheel to achieve that extra half thousandths, okay? If you've got a digital readout, you're simply going to be watching the digital readout at this point until that half thousandths clicks up. But using your knuckle as just a little knocker is another little secret in order to advance the dial carefully. Turn our machine off. If we were to project our edge finder down, we're in the exact center of that part in order to cut a slot. All right, we've got a more difficult job to tackle now. We've got a headspace gauge. For those of you that are familiar in the firearms industry, this is a headspace gauge for my new handheld personal defense weapon. Only joking. We need to bore this hole out a little bit larger in the center of this part, but wow, how do we find the center of it? We want to make sure that we've located it securely in the vise. We can put an additional V-block clamp or make a V-block clamp in here that holds it securely, but for just to show you how to dial it in, we're simply going to constrain it in the vise here snugly. We'll show you how to find it in a hurry. We've inserted a 3/8 collet in the top. We want to find the center of that hole quickly, so we're going to turn an end mill upside down, lower the quill in preparation for the final dialing. Okay, so we're going to advance our table, the X and Y axis, and we're just going to eyeball that end mill into the center of our part. Okay, looking left and right, down on the top, and let's see where we're at. Okay, that looks pretty close. Remember how we use the backside of the end mill to help align our vise prior to the dialing in operation. This is basically the same thing. It's a neat little trick that I learned over the years to facilitate rapid mounting and machining of specific parts. Another good way that you can do it, once we've made a location here with the end of our end mill, using our eyeball to say, yeah, that's pretty close, we can go ahead and move over on our dial now, loosen our lock nut, re-zero our dial, tighten the lock ring down now and go from side to side. Let's go ahead and give that a try. We've got 200,000 until we just come in contact with the side. Okay, we've got 390 thousandths from that center location. Go back to 0, and again, we're going to go the other direction now. There's 200 thousandths. Okay, and 180. So just by eyeballing it, I missed it about 10 thousandths, or double the thickness of the hair on your head. So let's go back to center now, where we think it was in the eyeball. We're pretty close, and let's install the dial indicator, and we'll bring it into exact location. We're going to change collets now. We're going to put in our 3/32 diameter collet. We're going to use a Starrett last word dial indicator. Anytime that we use the dial indicator, we want to secure it down. Okay, and we can take the dial with our little flipper, flip directions here. So now when we come in contact, okay, with our part, we're going to lower it down into the hole. Then we're going to take our finger and just advance it over to the side. We're going to preload the dial indicator a little bit. Okay, right to around 15. Then we're just going to rotate it by hand and watch the amount of offset. And I like to work it again as we did when we were dealing with tramming in the head on a north-south, east-west direction, or the x-axis and the y-axis. Okay, it's just a little bit easier to keep track in our head how much we want to dial in that part. So we'll take a reading here at the south end of things, and we've got 12 thousandths. We'll turn it over to the other side and see what we have there. And we're at 13, so we're going to take a thousandths adjustment out there. We'll turn over to this side. We're at 5. And we're at 20 there. So we'll go back to 10. Okay. Okay, and again, if you're running out of offset, go ahead and just preload the indicator again for another 15, 20 thousandths so we get plenty of contact as we rotate it around in the hole. We've got to have pressure with the dial indicator in order to get an accurate reading. Okay, we're just looking at the dial again in the north-south, east-west direction. We're making the adjustments with the travel dials on the mill to where that needle in rotation stays in the same location or within whatever tolerance we decide is appropriate for the task at hand. Okay, we're within about a half a thousandths now on that hole. We rotate it all the way around. So now we're ready for that boring operation. Our hole that we would bore would be concentric to our existing hole within about a half a thousandths, which for this intended job is pretty doggone close. Now we're going to step up to a little higher tech tool, and one that I strongly recommend you purchase, called a Blake coaxial indicator. You saw approximately how long it took us to dial this in. We showed you a couple of tricks by using the end mill inverted in the collet to roughly eyeball it in. Now watch how quickly it takes to bring into play with a coax indicator. I'm going to lower the bed a little bit. We can get our coax indicator in place. Raise the quill. Remove our existing indicator. and replace it with a 3/8 collet. All right, this is an example of our Blake coax indicator. Really a slick little product. I wish I had invented this. We've got different feeler points that we can use depending upon dialing in the inside or outside of a hole. This portion you see goes into our 3/8 collet, and this is a little hold bar to hold it firmly in place while we turn the machine on and make the necessary adjustments while the machine is running. Watch how quick and slick this particular product is. Insert it into the collet. Again, tighten it down. We don't want it falling out during the dialing in process. And we're simply going to lower the quill. There are necessary adjustments. We can tweak our adjustment out here just a little bit to preload the dial. Okay, we're going to shift the gear or shift the machine into back gear at this point. We want the indicator turning really slow. We don't want to turn it on at 5,000 RPM and burn the bearings out in it, okay? So we're going to shift into back gear. We're going to turn it at about 80 RPM at this stage of the game. Grab your safety glasses and watch how slick a coax indicator is in operation. All right, if we take a look, we can see that we had our original dial with the stare at last word in it about a 1/2 thousandths. Now, watch how quick and easy it is with the coax indicator. We're going to move the y-axis out. We can see our needle dial is just going nuts right now. Watch how easy it is to pull it back into spec. Simply turn it until that needle just about comes to a stop. All right, if we go too far the other direction, again, the needle starts to go nuts. So it's really fast and easy to bring it back into play. Very slowly and precisely till all needle movement stops. Now let's do it on the x-axis, and you can see what happens. Right, needle's going nuts. We'll bring it back into play. Okay, and there we are within about 1/10,000th of an inch of being perfectly dialed in above the bore in this specific part. The coax indicator, in my opinion, is one of the most useful tools that you can buy if you're going to be doing a lot of dial indicating work, either on interior or exterior diameter parts. All right, we've reviewed a lot of the techniques on how to properly set up the workpiece, how to use the edge finder, how to square a block of material. Remember to remove the burrs. Remember the trick with the WD-40 on the parallels. That sucks them up against the vice jaws, keeps the dirt and debris out from behind them, keeps them from shifting as we remove the workpiece to interchange it with another one. We showed you how the coax indicator works. We showed you some different methods that allow you to make the ideal setup. Keep in mind rigidity is very important. Keep in mind that the amount of cutter protruding from the collet is again very important. We cannot gain in one area and lose in another. We have to work together. We have to have a good solid work support. We have to have the cutter mounted rigidly in the collet, in the tool holder, or in the chuck. Remember, when you're using an edge finder diameters, 9 out of 10 of them are going to be 200 thousandths in diameter. When we come up against the workpiece, we want to add an additional 100 thousandths to whatever the half dimension is in order to bring the spindle and quill directly to the center line of that existing part. All right, that's pretty well a wrap on setups. Now let's move on to our next phase. let's take a look at the different types of cutters that we're likely to encounter for the vertical milling machine. There's quite a variety. Let's start off with the 3/8 diameter shanks. This is referred to as the shank of the cutter. This is what we are holding in the tool holder. Whether it's a standard tool holder, a collet, a drill chuck, this is what it's gauged by, and they come in a variety of sizes from 1/4 inch, 3/8, half, 5/8, 3/4, etc., all the way up the scale. This particular cutter is a 4-flute, extra long flute length. Okay, so you can see the depth here, and I'll show you as a comparison what a standard depth looks like. Okay, you can see the two. This has about a 5/8 of an inch cutting depth along the periphery of the cutter, and this has about 1.5 inches. This is really a popular cutter if you're facing across the thick part or we have to get into a deep hole and machine down on the sides. Now let's look at the end of the cutters because we can see a difference there as well. This is what we call a 4-flute center cutting cutter. You can see that in the center the cutting edge runs clear through. We can plunge with this particular cutter. You'll see a lot of 2-flute cutters are a center cutting flute as well, so we can plunge with those. On this particular end mill, this is a non-center cutting mill. You can see the little center drilled hole in the center of it that they use when they set up and grind or sharpen this particular end mill. So this one is strictly for working with the periphery of the cutter or cutting and enlarging an existing slot. We cannot plunge with this type of an end mill. All right, this is a 1/2 inch solid carbide ball end mill. And if we were to look at the profile of this cutter, we can see that it resembles a ball or a hemisphere. Okay, this is used for decorative cuts, cutting a slot or a flute that we want to have a radiused bottom in. Very popular cutter style, very expensive cutter in solid carbide. You want to protect your cutters when you have solid carbide around, as they're quite an investment. Don't let them get chipped or dinked. This is a 2-flute cutter, and again, if we were to look at the end of it, this is a plunging type cutter as well. And by plunging, I mean from the vertical position, we can plunge down into the material while the tool is turning and cut. This is a double-ended mill, meaning we have cutting flutes on both ends of the mill. This is a single-end mill. Okay, it'll only cut on one end. You get more bang for your buck often by buying a double-ended end mill. This is a 5/8 end mill, 4-flute. We'll look at the ends of it. Center cutting or non-center cutting? You tell me. We've had a little lesson on that earlier. For those of you that guessed center cutting or plungeable mill, you guessed it right on both ends. Okay, 4-flute cutter gives us a lot of surface area when we're cutting. Good chip removal with this particular type of cutter. You'll also notice on a lot of the end mills what we call a weld-on flat. This is very important depending upon the type of tool holder that we're using. We'll show you a little bit later under tool holders where this comes into play. We've got a 3/4 inch solid carbide end mill, and you can see the gold color between the flutes here. This particular solid carbide end mill was what we call tin coated afterwards, and it's a hardening process that goes over the outside, ensuring a little bit longer cutter life. However, when the cutter gets dull and we grind through the tin coating, it's simply there for effect and to remind us how much this particular cutter cost when we purchased it originally. This is an example of a form cutter. This was a 2-flute center cutting end mill. You can see again on the close-up that we can also plunge with this type of end mill. We've had this end mill special ground for a radius in the center, and we'll show you an example of what type of profile this cuts. You can send your different cutters off to the different grinding houses and have your own form cutters done for specific applications in the shop. Important considerations in form cutters, as in this case, if we have a radius from the end of the end mill to the center of the radius. So when we plot this on a piece of material, we know how far to move the bed in the z-axis in order to center up on the radius and get this form tool to work properly for us. This is another example of a form tool. It's called a corner rounding mill. This does a lot of decorative work if we're going to profile a round or square or rectangular part and produce a nice radius edge. Very useful tool. Gives us a real artistic look to the finished product. Non-center cutting. This tool strictly is working around the periphery of the part to be able to cut a radius edge. And they come in different sizes. You'll see on the end mill this is a 1/4 inch radius. Okay, so that's the style. This particular one is a high-speed steel corner rounding end mill made by the folks at Keo. Another example of a special form cutter is this radius cutter, and you can see that we made it from a 3/4 inch end mill. It's got a special profile for cutting a radiused baffle. This is a very delicate tool. We use this in the production of our unique triple baffle quick discharge muzzle brakes. Again, you'll see a number on the side that shows us from the bottom of the cutter to the center of the radius how many thousandths we need to move in the Z-axis in order to have this cutter and radius centered in our part. So keep those tips in mind when you're having your form cutters done. This is another specialty cutter. It's a 90-degree, we like to call it a V-block cutter. We manufacture a lot of V-blocks for tooling, fixtures, and the different accessories for the firearms industry. Again, a specialized cutter, a 2-flute cutter. We can plunge with this. It's a center cut, so if we wanted to work in the vertical mode, we can come through and plunge to a specific depth. We'll show you how to properly cut a V-block for tooling or for personal use by cutting a slot or channel first and then coming back with our form tool in order to cut that 90-degree V-block. This is an example of a Woodruff cutter. Again, a specialty cutter. This tool is used for cutting slots or keyways. There's a variety of different sizes. The folks at Keo are probably some of the largest manufacturers of specific Woodruff style cutters. Now you'll notice the number of teeth that we have on this style cutter. For those of you that are already up to speed, they require turning this particular cutter at a very slow RPM. So we would simply engage the milling machine in back gear any time that we were to use a Woodruff style cutter due to the number of cutting teeth or flutes, if you will. The normal cutters that we'll deal with in an end mill are usually 2, 3, and 4 flute, depending upon the type of material that we will be machining. Here's an example of a rather large ball end mill. Again, this was a specialty cutter that we had ground. It's a Brubaker, very good quality cutter. Center cutting. You'll see that the 4 of the 6 flutes here have been relieved on the sides, so we're only going to be plunging with the 2 in the center. So this is going to produce an 1.375" radius in whatever it is that we are machining. A very expensive cutter if you had to go out and buy it. A good tip is to, if you live in an area where there's aircraft manufacturing or large machining facilities like Rohr Industries, Boeing, etc., take the time to go through their scrap pile. When their cutters get dull, chipped, or broken, you can often buy these for literally pennies on the pound and take them over and have them reground and use them in your machine shop at a tremendous savings. They're well worth your while for doing a lot of specialty and form cutters. I've done that over the years and have acquired quite a collection of very expensive cutters if I would have to go purchase them new. This is what's called a fly cutter. Fly cutter is a very useful tool in the machine shop, especially if we're surfacing a lot of material. We've got a lathe tool bit mounted in a special holder that you can make on the lathe in the mill, and it runs in the vertical position this way, and as it turns, we're just shaving off material. It's not for removing a big bulk of material, it's simply for surfacing in one smooth pass, making a flat surface, prepping our work for secondary or third operations. Okay? Last cutter we have to look at looks more like a horizontal mill cutter. Yet this is a special horizontal mill or stub arbor that we can purchase. It's got the R8 Collet profile on it. And this goes up into our spindle quill. This is a lock nut on the bottom that we simply unscrew, and we can space or put different types of horizontal cutters in this, allowing us a little more versatility in the vertical mill by being able to cut a fluted barrel, let's say, or put different flutes in a part for aesthetic value or for cooling value. Really a handy tool to have. They're going to run you $35 or $40 out of most of the popular tooling catalogs. All right, that's a pretty good overview of a variety of cutters that you can expect to use and find in your average machine shop. But before we get started making chips, let's move on and have a look at our next principle. In order to hold our tool rigidly in a vertical mill, some very bright guys dreamed up some ingenious methods for us. Probably the most popular is the use of our R8 collets. As I mentioned earlier, we always want to buy good quality collets. Hardinge, good American-made, Brown and Sharp collets. They'll come in a set of 15, 20 collets depending upon the increments that you want to work them with. By far the most popular would be 1/8, 3/32, 5/16, 3/8, half, 5/8, and 3/4. You'll see the numbers in most cases stamped on top of the collet. This particular collet is made by the folks at Hardinge, and it's a 3/8 diameter. So this is going to take all of our 3/8 type end mills, drills, reamers, etc. Here's another Hardinge in a 3/4. Okay, this is going to take a pretty good size end mill. We'll use this collet if we're doing a lot of roughing material. Some folks get a little excited and feel that the end mill has the possibility or potential of slipping in a collet, and they've come up with an interesting concept as well called a tool holder. This is a very expensive tool holder made by the folks at AccuPro. Very rigid R8 collet design, machined integral with a heavy boss and a 3/4 inch precision hole that has been ground. It will accept our 3/4 inch end mill. You can see that we've got our flat on the top of it and our large set screw here. So in order to apply this correctly, we simply loosen the set screw, push our end mill into place, tighten our set screw down against the flat that we showed you earlier, and that locks our end mill rigidly in place. It's very important when we apply a end mill to the tool holder or the collet that we choke it up really close. We don't want a tremendous length protruding from the tool holder. This makes for a very unrigid setup. In some applications it may be necessary to extend the cutter out farther because we've got a deep hole to machine into or we've got a boss that is interrupting that. For that type of machine work, you cannot use this type of tool holder because it is regulated by the flat that we see on the cutter. It's a big advantage of a collet system in my opinion, because with a collet it allows us to be able to infinitely adjust the length or depth of our tool. Ideally, if we were going to use this V-block form cutter that we have here, we'd want to choke it up really close to the collet. Okay, you can see we've got it choked up right on the end there. But if we have a deep hole to reach or a hard to get place, we can infinitely pull this collet out within reason and expose more of the cutter. Remember, we're losing a little bit of rigidity, but we still need to get into the deep hole to cut, so some sacrifices are going to have to be made. A good rule of thumb when trying to determine how much cutter we can expose from the collet is 1.5 times the diameter of the shank that we are using. Okay, and again, this is going to apply to the different types of materials that we are using, the depth and feed rate of the cut that we're doing. Anytime that we extend the cutter out from the collet or the tool holder, keep in mind we want to slow down our feed rate a little bit, take a minute amount of material off because we have lost a little bit of rigidity in the holding process. So that's a good versatile way to deal with a collet system. Again, with the big ball end mill properly installed, we would want it butted up right against the end of the collet. In some cases we can extend it out, but not very far. When we're dealing with form tools, depending upon the tooling that we've designed, we always want to keep our form tool as rigid as possible. We've got a special form that's been ground into the cutter, allowing us a very precise profile in the milling operation. We've spent quite a bit of money to have this profile machined, so we don't want to damage or break the cutter. Keep that in mind as well in your machining. Another useful tool that we'll be using in the mill is a drill chuck. This particular chuck is made by the folks at Albrecht. It's called an Albrecht keyless chuck. For those of you that purchased our instructional course on the lathe, you'll see that we used an Albrecht keyless chuck in the tailstock. It's got a big knurled band, and we simply, with a twisting action of the wrist, we can tighten the jaws around our drill or end mill. We'll show you some neat tips and tricks on using an end mill in the drill chuck in special applications. It's not really rigid enough by comparison to a tool holder or a collet, but in some applications it can be quite useful when we want to machine or recess or counterbore a pocket at the same time we're using a center drill. So having good chucks, spend the money on them. Don't buy a cheap imported chuck. Get a good American-made or European chuck like an Albrecht or a Jacobs to complete your selection of accessories for the mill. All right, that pretty well covers the tool holders. Now let's take a look at some of the different types of cuts that these end mills and profile cutters will produce. We've shown you a variety of cutters that you may expect to find in a machine shop. Now let's take a look at what those cutters are capable of and the different profiles that they machine. We've installed a fly cutter and we've got a block of aluminum mounted in the vise. We'll show you how quickly and efficiently a fly cutter surfaces a piece of material. Okay, we'll back our fly cutter out until we just are in contact with the work, cast off of it. We're going to take about a 5/1000th pass. Anytime that you're working with aluminum, a really cost-effective lubricant for machining aluminum is Old WD-40. With a very smooth advance of the cutter, we'll start surfacing across our part. Remember how we showed you to advance the mill by rotating the hand wheel in the palm of your hand. Very important for producing a smooth, uniform cut. You can see how smooth the rotation is. Okay, now we'll pause a little bit. We'll show you a jerky rotation, of which you do not want to do. Okay, that'll be evident in the finished cut. All right, you can see that particular part's about 3.5 inches wide, and we can completely surface it in one pass with the fly cutter. If we were to have a 3/8 end mill and try and surface something that wide, we'd be there a week trying to do it. Now let's take a look at a different type of cutter that we can go across to surface or face the end of our block while it is mounted in the vise. Take our 3/4 inch solid carbide center cutting 4-flute end mill. We ran the fly cutter at 660 RPM. We're going to increase the RPM to 1115. Bring the quill down, center our cutter on the part, lock the quill down. This will be a facing operation across the end of our part. We're working in the what axis right now. For those of you that said y-axis, you're correct. We've dial indicated our vise in, so anytime that we work off of the y-axis, the surface that we are machining is absolutely, positively 90 degrees to the x-axis. All right, there's our facing operation that's complete. We've surfaced the top of the plate. We've faced an end of it. Now let's put a little gingerbread on by using our corner rounding end mill. Remember to always choke our cutters up nice and tight unless we're in a special application that we need the cutter to protrude farther from the collet or the tool holder. Now look closely as we rotate the cutter, and you can see the relief angle right on the end of my finger here. This is the top of the radius in a corner rounding tool. We do not want to cut below that. So we're going to take the corner of our corner rounding end mill, offset it enough, and just bring it down in contact with the top of our workpiece. Next, we're going to move down to the knee, and in the Z-axis, we are going to lower the bed 5/1000 of an inch, creating a 5/1000 gap between the top cutting edge of the cutter and our workpiece. Back the tool away from our work and slowly engage it. We're going to need to watch in two directions now as we apply the cutting depth. Okay. Come across in this fashion. Again, give the tool a little shot of WD-40. Acts as a very good lubricant. You can see the very attractive rounded edge that we're applying to our workpiece. Okay, looks pretty sharp. Now let me show you the incorrect way to do that. If we were to cut too deep on the top mode, we're going to raise the bed up just a little bit where we actually start cutting in two directions. We're going to cut a little deep. Okay, you can see where we've cut too deep along the top line here. This makes for a very poor decorative effect, and this is an improper radius. We want to have a nice, smooth, continuous radius that you see here that just flows from the top of the part down to the bottom edge. All right, we'll install one of our AccuPro tool holders, and let's take a look at what a form tool does on the end of our aluminum slab. Make sure we don't have any aluminum chips or debris on our tool holder as we insert it into the spindle. All right, let's take a look at what a form cutter does now. Just like a giant router bit, for those of you that may be woodworkers, our form tool is going to start profiling now our block of aluminum to our finished dimension. We'll give it a little shot of WD-40 there and improve our surface finish. The nice thing about machining aluminum is you can really get a nice surface finish on it. For a final pass in aluminum, I recommend a climb cut. We'll go into that a little bit farther into the series. But you can see the special profile that we've machined now. This particular form tool is for building a special wrench that we do. Let's move our cutter out of the way and see if we can give you just a little bit better view. There you go. How's that look on a close-up? It's a nice concave profile there, like I say, for a special wrench that we do. All right, let's change cutters now and go to a Woodruff cutter. Remember, the Woodruff cutter now has got considerably more teeth than this two-flute cutter, so what are we going to need to do? You guessed it, slow the cutter speed down tremendously. We're going to go ahead and shift the machine into back gear. We'll use a 1/2 inch collet. We're going to turn the Woodruff cutter about 135 RPM in back gear. We're going to put a Woodruff key in something, a shaft or another part. Remember, we index the top in. We go from out to in on our exchange lever, and we turn it in reverse in the back gear mode. Give it a little shot of WD-40. Lower our cutter to our workpiece just a little bit. Let's take a look at the effects of a Woodruff cutter. Okay, now these types of cutters have a tendency to load up. So take them out and clean them from time to time. Give them another shot of lube. You can use your air hose on them. Blow those chips out. All right, let's take a look at what we've done. I'll grab the air hose and I'll show you the proper way to use air on a milling machine. You can have a pressure regulator on the hose line or very gently use our air hose to blow the chips away. Turn your machine off. All right, you can see the beginning of a keyway that we're just starting to machine into the end of the aluminum block using a Woodruff cutter. Now let's go on to bigger and better cutters. Let's go ahead and make a little V-block pass. But first, what are the important things that we must remember when we shift from back gear to direct drive? We make the change on top of the headstock. We switch our lever from in to out, and then we take our wrench and turn it until we hear that clunking sound of the gears dropping into mesh again. Otherwise, if we turn it on, we're going to have a terrible crashing gear noise before those gears align themselves. All right, let's use a center cutting 3/8 end mill this time. Remember we talked earlier about a center cutting mill or a mill that we can plunge with versus a non-center cutting mill. This is a 4-flute center cutting in the AccuPro tool holder. Okay, anytime that we're going to use the end mill in a plunge mode, we're going to go ahead and plunge using the Z-axis or by raising the knee in order to plunge the cutter into the workpiece. We're going to turn it around 1115 RPM for a 3/8 4-flute cutter. Little shot of WD-40. Then we slowly start raising the bed. You can see that it starts to cut immediately. Another shot of lube, plunge to whatever depth we want. Now we're ready to machine our slot. Break through onto the other side, raise the Z-axis, and we'll take a second pass. Taking about 100 thousandths in this particular pass. Got a pretty healthy feed rate. You can see the chips boiling out from around the cutter. Remember we talked earlier about listening to the machine. Hear how smooth the machine is running. It's not going clunkety clunkety clunk. That's telling us we're turning at about the right RPM. We've got a feed rate that is consistent with the RPM that we're turning. Anytime the cutter is going clunk, 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 trying to grab or push the work out of the way, it's telling us usually that one, the feed rate is too fast or the RPM is too slow. We'll take a third pass again, about another 100 thousandths, and then we're ready to try our big dovetail cutter. All right, we've made the last pass using a 3/8 end mill. We can see we've got a lot of chip buildup around our part. Do we want to use our finger to go ahead and wipe those chips off? No way. Grab an acid brush, a toothbrush, use a little bit of air, whatever, but do not, under any circumstances, stick your finger in around the cutter while it's moving. We've developed a pretty sharp edge along the edge of the channel that we've machined there. If you're to run your finger across it, it's going to cut you like a serrated knife. So always use a little acid brush or a rag or towel when you're wiping it off, and be very gentle. All right, now let's throw in our special V-block cutter and see what that profile looks like. V-block cutter has a 3/4 inch shank on it. So what size collet are we going to install? You guessed it, a 3/4 inch collet. Choke the cutter up nice and tight to the top of the collet. Bring it down in contact with our work. We're going to climb cut on this pass. We're going to cut the right-hand side of the slot first. Got an appropriate feed rate. We're taking probably about 20 thousandths off in this initial pass. We'll index over on the other side and take an equal amount off. Shot of WD-40 as a lubricant. You can see how the chips are kind of coming off like brass out of a machine gun. It's another important reason to be wearing your safety glasses at all times. All right, if we were machining a little V-block for a piece of tooling or fixture, we'd be just about complete at this stage of the game. Grab our acid brush, clean it off, and we'll set a cutter in there to show you how it works. All right, if we're going to build a little cutter to hold some round stock, you can see that that V-block works just perfect. We can run a little overarm clamp to the side of it to hold it in place. We can drill and tap it, whatever the case may need. All right, let's see what else we have. Let's go ahead and do some ball end mill work. You'll be called upon to do that from time to time. Remember, radiuses in the corners, just like turning on the lathe, are very important to the strength and structural integrity of the part. So anytime that we can machine a radius into a slot or a groove somewhere, we're simply increasing the strength of that specific part, eliminating the possibility of a fracture or a stress crack if the part's going to be put to hard use somewhere. We're going to go ahead and use our solid carbide 2-flute 1/2 inch ball end mill. Can we plunge with this particular cutter or not? You bet. It's a 2-flute center cutting. We can plunge. We'll show you an example of that in just a second. We'll go ahead and pick up the same path that we did with the V-block cutter. Come down until we spot off. Shot of WD-40. Go ahead and raise the knee. Whatever depth we want there, pull our cutter out. We're now ready to take a pretty heavy cut. Anytime that we're working in one direction on the mill when we're cutting, it's a good idea to go ahead and lock your gibs down in the opposite direction. That way we're not pulling against the lead screws, and it gives us a truer, straighter cut. Okay, we can index our cutter over now for final pass. We'll go ahead and climb cut in this direction. Clean up both sides. We'll clean it off and show you what a radiused ball end mill profile looks like. Remember, we've got a nice uniform rotation of the hand wheel on the y-axis. Just let it slip through the palm of our hand. Get some of the chips out of the way so you can see a little better, and another shot of WD-40, and we're just about complete. I'll try and give you a close-up view there so you can see that nice slot. All right. That's a pretty good example of the types of profiles and different machining operations that we can do from basic cutters, form cutters, and fly cutters. An important thing to keep in mind is the proper care of the cutter. You can invest a small fortune in cutters. Good end mills are going to run you 15, 16 bucks a piece in the 1/4 and 3/8 diameters. You can spend up to $100 for a good solid carbide 3/4 inch end mill, depending upon where you purchase it. Your corner rounding end mills are also very expensive, $25, $30, depending upon the radius that you're using. So we want to protect these tools. When we set them in our drawer, we don't want to set them together where they're going to, and I'll show you with the set of our R8 collets, they don't want to be clattering and beating themselves together. They've got very sharp, delicate edges on them, and if they clatter together and chip and dull themselves in your toolbox, you're not going to get the maximum performance out of the cutter. You're going to constantly have cutters in the shop for resharpening and grinding, and this is more money out of your pocket rather than in your bank account. So keep the cutters separated. You can make a little wooden block, cut some slots in them so each cutter has its place and it isn't rotating or sliding back and forth in your toolbox. All right, let me remove the block from the vise, clean it off, and let's take a look at some of the cuts that you've just witnessed. The top surface we machined with our fly cutter. You can see in the beginning as I moved my finger across, we had a nice, smooth, uniform rotation of the hand wheel on the bed. When we went to the choppy mode, you can see the big score mark that was left as we rotated the handle down. This is what happens if you're not careful and have a smooth stroke. So keep that hand wheel rotating like a greased ball bearing in the palm of your hand. Next, we have a slot that we machined with the ball end mill. You can see it's a nice deep radius channel. We've got our form cutter profile that we machined on the end. It's a good view of that. We've also got our keyway that we machined with the, you guessed it, Woodruff cutter. Woodruff cutters are used to machine slots and keyways. We've got a nice radius edge that we did with the corner rounding end mill. All right, we've shown you a lot of the different cutting operations using specific profile cutters, Woodruff cutters, end mills, ball mills. Now it's time to move on and take a look at the different types of materials that you may be expected to machine in the shop.
Attention, gun owners, collectors, hobby gunsmiths, FFL dealers, and professional gunsmiths. The American Gunsmithing Institute offers you comprehensive training and information through our exclusive instructional videos. AGI's complete line of how-to gunsmithing kits will give you the results you're looking for, whether you're refinishing a stock or glass bedding a rifle. Each kit comes complete with AGI-approved products and a video instruction manual featuring a master gunsmith. Whether the process is as simple as tactical spray coating or as involved as parkerizing, we guide you step by step as only AGI can, giving you the tips and techniques you need to avoid mistakes and get professional results. In the AGI Armorers series, each course covers a specific firearm. We give a brief overview of the history, demonstrate the design and function using cutaways, and guide you step by step through complete disassembly and reassembly down to the last part. We also show proper cleaning and lubrication methods, troubleshooting tips, repair techniques, and review available accessories. No other video will give you this level of instruction on one specific firearm. We offer courses on all the popular makes and models. Want to learn more about general gunsmithing techniques? In AGI's complete practical gunsmithing course, we show you how to set up your shop, and then we cover step by step the most common gunsmithing projects. In over 4 hours of exclusive video, a master gunsmith will teach you precision scope mounting, sight installation, stock repair, cold bluing, glass bedding, recoil pad installation, how to remove a dent from a shotgun barrel, and many other tricks of the trade. If you're interested in becoming a gunsmith, the American Gunsmithing Institute is internationally recognized for our professional gunsmithing course. It contains over 100 hours of detailed instruction on 56 videotapes. Instructor Robert H. Dunlap has over 30 years of professional gunsmithing experience and has taught professionally for 20 years at one of the nation's top gunsmithing schools. He will guide you step by step through the design, troubleshooting, and repair of all types of pistols, revolvers, shotguns, rifles, and .22s. Our close-up video techniques combined with Mr. Dunlap's exclusive knowledge and unique teaching methods provide you the opportunity to become an AGI tested, certified gunsmith. Whatever your gunsmithing needs, AGI can provide you with the knowledge and materials you need to successfully customize, repair, and refinish your firearms. For a complete catalog featuring all of the AGI products, simply contact the American Gunsmithing Institute at 1325 Imola Avenue West, number 504, Napa, California 94559, or call 1-800-797-0867. Or you can browse through our color catalog with images from the actual videos at our website. Get online with the American Gunsmithing Institute at http://www.americangunsmith.com.